Okay, let's talk center of mass and moment of inertia. First of all, center of mass is exactly what it sounds like it is. It's where all of the mass can be thought to be. And that's kind of the important thing. So if I have something, first of all, let's talk about regular shaped objects. A regular shaped object, if I had something like this, some type of long rectangular solid, the center of mass is going to be right there. I can treat as if all the mass actually acted at that individual point. Now, so I don't care what kind of regular shape, if you have a circle, that's the center of the mass. If you have a triangle, the center of the mass is going to be in there, but maybe a little bit lower than that. Center mass is important in stability. For example, you can lean over stability. There you go. If I have something like that, the Leaning Tower of Pisa. The Leaning Tower of Pisa looks like this, but the center of mass is still over the footprint of the building. If the center of mass gets outside of the footprint of the building's going to come tumbling down. So for example, if I have a truck on a banked road like this, it's got wheels here and wheels here. As long as the center of mass is between those wheels, you're okay. If you get to the point where the center of mass is, those are your wheels, that's your wheel. If the center of mass is here, let's say for example the truck is really top heavy, if the center of mass becomes here, it's tipping. So center of mass is kind of important with that. Now, if I have an irregular shaped object, to actually calculate what the center of mass is, really is going to take some math, because what you're going to have to do is you're going to have to sum the individual masses over a large area. So therefore you're talking really calculus at some point in time to do it. Right now all you need to understand is it is the point where all of the mass could be thought to act. So if I had something like this, center mass would be closer to this side. A ketchup bottle. The ketchup bottle has a very low center of mass. That's the reason it's really, really hard to knock over. You'll see the fair things where they'll do this, and they look amazingly like they're easy to do. They put 3 usually metal cylinders like this, and they stack them up like this, and they tell you if you can knock them over, you win, some stuffed animal that doesn't want to cost. What they do is they add a lot of weight to the bottom of these, which lowers the center mass, so these are extremely hard to knock over by adding weight. So weight. What you could expect to is probably to be able to guess where the center of mass of an object's going to be. If it's a regular object, it's right in the geometric center. So regular, geometric center. Irregular, use your head. You think if you have something that looks like this, it's going to be right there. If you have something that looks like this, it's going to be closer to there somewhere. So kind of use your brain on it. Now, while we're talking about that, let's talk about moment of inertia. Now, we talked about inertia in a linear sense or translational sense. For moment of inertia, we're going to use capital I. For this course, it's only going to be a number. It's not going to be something you have to calculate. Eventually, you may have to calculate it. There's a formula for every shape. First of all, let's make sure we know what it is. Let's go to mass. Mass has inertia. Or an object has inertia because it has mass. And what this measures is how hard to accelerate the object in a linear fashion. Well, moment of inertia, I'm just going to start using I because it's easier to write. Moment of inertia is how hard it is to accelerate rotationally. In other words, how hard is it to make something spin? And it depends upon two things. It depends on how the mass is distributed. Now, for normal shapes, there's all sorts of different distributed. There's way too many letters in that. You can correct the spelling of your own. There's a wiggly red line. Tell you it's spelled wrong. So it depends on how the mass is. So for a disk, and again, you don't have to know these formulas. It's 1/2 mr squared. For something like a, if memory serves me correct, something like a dumbbell, looks like this with the weights out here, its I is equal to 1/12 mr squared. Now, you're not going to have to make those calculations, but you are going to have to use those because moment of inertia tells you how easy something spins. Low moment of inertia, it's going to spin real easy. High moment of inertia, it's not going to spin very well. And we will tie it into torque is probably the biggest thing. And we talked about torque briefly before. Torque is force times lever arm. We'll get into that a lot more. But we need to understand moment of inertia in order to get into rotational dynamics. Remember, we've done linear dynamics. Linear dynamics, we're in love with F is equal to ma. It kind of governs our world in the linear word. F is equal to ma. Well, rotationally, there's something also that corresponds to that, but it's torque. And torque is equal to, let's leave that for another day. And you'll get another video on it.